Okay, we're good. All right, so example 8, use the definition of continuity at a point. So that's basically your hint that you need to justify using the three-step definition. Now look, this is kind of broad and vague. Discuss the continuity of the function over its entire domain. And then it does say justify. Now, you wouldn't necessarily be given a question that's this wide open, whether it's on my test or the actual AP exam. It's usually partitioned into sections so that you can answer one at a time that leads you to it. But this is kind of a nice summary of what we've talked about so far, minus vertical asymptotes. Begin with the end in mind. We need to make some kind of statement at the end, or a blanket statement, if you will. Speaking of blanket statements, there are blankets in that right cabinet door if you get cold. We need to make some statement at the end about the continuity of the function overall, but we need to collect our evidence before we make that statement. So let's just look at the pieces themselves. X plus 2, that's a line, right? Domain is all real numbers. Continuity is everywhere. X squared over 2, that's a parabola. It's like 1/2 x squared. Continuous everywhere. Domain is all real numbers. 2 is over an interval, not at a point. Over an interval, it's just a horizontal line. Also continuous everywhere. Therefore, the only place where this piecewise function may not be continuous is at -2, where it switches from line to parabola, and then at +2, where it switches from parabola to horizontal line. Do you agree? It's the only place, because the polynomial pieces themselves are continuous everywhere. So now we know to check those places, and we're going to do that with the three-step definition. So if it is a problem like this and you're doing multiple things, remember the goal is to not just get the right answer, but to communicate how you're doing it. So what I would say is label it. Get in the habit of labeling things. So let's go from left to right. I'm going to first say at x equals -2 colon. Usually when you put a colon, it means, hey, I'm about to do work for this. Now, if you want, you could put it underneath there. Let's go ahead and get our machinery up and running. Road, bridge, road. The limit as x goes to -2 from the left of f of -2, and the limit as x goes to -2 from the right of f. And then I'm going to evaluate those vertically, okay? Now, the limit from the left of -2, which piece do I use, top, middle, or bottom? Top, okay? Now, I don't really do your homework. I don't even bother writing down the x plus 2. I just know that that's the piece I'm using to the left of -2, and I'll just plug in for x. What is -2 plus 2? 0. So I would just put a 0 now underneath there. But let me tell you what a lot of students feel comfortable doing. Because to the left of 2, right, less than or -2, it is x plus 2. They want to write that down before they plug in, which is fine. But don't do it like this. Don't put x plus 2 and then plug in a -2 and get 0. What's wrong with that? Right. You're missing something in front of the x plus 2. Because when you work vertically without equal signs, the equality is implied. And anytime you equate two things, they have to be equal. So x plus 2 is not equal to the limit of f as x goes to -2, nor is it equal to 0. If you want to put the x plus 2 in there, that's fine. You just need to have in front of it the limit as x goes to -2 from the left, and then I would put it in parentheses. In other words, that's the piece that you're using. And if it helps you to see it, that's fine. F of -2, which piece? Top, middle, or bottom? The middle. Now, again, if you write x squared over 2 and then plug in your -2, you're going to get 4 over 2, which is 2. There's really not even a good way to fix that, because what do you put in front of x squared over 2? It's not a limit, okay? f of negative 2 is not x squared over 2. So I wouldn't put that at all. If you want to put above there, like f of x equals x squared over 2, you can. But less is more in this case. So we're looking for the equal sign. It is, you could do this, negative 2 squared over 2. You could do that, right? And that kind of indicates that you plugged it into the middle piece. And then just be careful with your negatives. Now, if this were truly my own doing and I was checking continuity on my own, they didn't give me road, bridge, road as part A, B, and C to evaluate. Do I even need to, at this point, evaluate the limit from the right of negative 2? No, because when you're checking for continuity on your own, the game is over if any one of them fails to exist or any two of them exist and aren't equal, correct? Yeah, just if you're checking for continuity. So now I would say, note to myself, if you had to justify, f is not continuous at x equals negative 2, comma, because, and now you could say 0 does not equal 2. Boom. That's just the continuity question. But maybe you're interested in what type of discontinuity there is, right? If you're interested in the type of discontinuity, now maybe the limit from the right of negative 2 is something you're interested in. So let's go ahead and find that, but I'll find that in a different flavor just because it's not required for what I want to do. The limit from the right of negative 2 is greater than negative 2, which is which piece? Top, middle, or bottom? It's the bottom, right? It looks like it's a less than, yes? Because it is, but when you write negative 2 is less than x, that's the same as x is greater than negative 2, right? So you're just to the right of negative 2. You don't want to go so far to the right of negative 2 that you're using that piece, right? This is just to the right, just to the left. So by direct substitution, we get 4 as well. I'm sorry, 4 divided by 2, which is 2. Now, just for kicks and giggles, does that make sense? In other words, if you look at this right away, when you read it from the inside out, x is greater than or equal to negative 2. Bless you. You know then that the right-sided limit and the function value are the same because they're built by the same company, if you will, right? They're both defined by that piece. What type of discontinuity is it then, just for kicks and giggles? It's a jump, okay? And again, it has nothing to do with the function value. It's simply because 0 doesn't equal 2. The limit from the left doesn't equal the limit from the right. So we got to jump there. I might just make that note to myself. Jump at, would we say at the point 0, 0 or at the point 0, 2 or negative 2, comma something? Well, remember, if it's just a jump, we don't give any y value, right? Because there could be, yeah, there could be several locations. So we just say at x equals. All right. Now we look at the next point of exchange, which is at 2. So at x equals 2, colon. Let's get our machinery up and running. The limit is x goes to 2 from the left of f, f of 2, and the limit is x goes to 2 from the right of f. I like to write those down first because you're focusing on the notation. I mean, that's important. Get it wrong, you can lose points. And now once it's set up, I can just come back and evaluate it. All right, from the left of positive 2 is which piece, top, middle, or bottom? It's the middle, right? And again, just looking at it, hey, the limit from the left of 2 and the function value at 2, it's going to be the same because they're built by the same company. It's the middle piece. So what is it? Well, when I plug it in, I get 4 divided by 2. This is 2 and that's 2. That's the easiest way to do it. I personally wouldn't bother writing the limit as x goes to 2 from the left of x squared over 2. you can, but I would just say, oh, it's this piece, let's plug in for x. Okay. If the limit's there, it has variables. If the limit's not there, it's a constant. And then the limit from the right of 2, that's the bottom, greater than 2, is 2. Oh, if you had to justify this point, what would you say? Continuous, yes or no? Yes, okay. So f is continuous at x equals 2, comma, because, and now again, the easiest way, since everything is already labeled up above, is it since 2 equals 2? 2 equals 2 equals 2. Good. Because I have the two one-sided limits labeled separately, I need to say 2 equals 2 equals 2. You're equating all three by way of 2, right? Now, you look for the equal sign in the equation, right? Yeah, so here's the less than is left of, and because it's less than or equal to, you know, there's the function value as well, right? So you can tell right away that the left-sided limit and the function value, because it's less than or equal to, are the same. All right. All right. Now, if you happen to have the general limit labeled up above as 2 and f of 2 labeled as 2, then you could say since 2 equals 2. But in general, I don't even teach that. So there you go. All right. So is that it? There's no built-in discontinuities in any of the pieces. And of the two possible locations, only one of them is a discontinuity. So now we'll make a blanket statement. So f is continuous for all x not equal to -2. Yeah, take a look at that. Is that pretty good dessert right there? After lunch? Y'all seen that upside down A? Some of y'all have, no? Yeah, it is a legitimate mathematical symbol. It means for all. Yeah, upside down capital A means for all. Feel free to use it. You can actually write out the words for all, or you can use the inverted capital A. For all x not equal to -2, where we know the function happens to have a jump discontinuity. What would the domain of the function be, just for kicks and giggles? Is -2 in the domain? Ah, very good. No, that's all right. That's why I asked it. The domain is all real numbers. Okay. So you can have a discontinuity at a point where the function's defined, right? Yeah. That function value just doesn't help make it continuous. All right. All right. We're in here till we got plenty of time. One more. This next problem here will allow you to get quite a few more in your worksheet done. We're not going to finish today. We'll finish tomorrow. So the first worksheet will be due on Monday by 9 a.m. into Canvas. All right. We will quiz tomorrow. Yeah, we will quiz tomorrow. Sure. Yeah, everything, and maybe some unit circle stuff. Watch. I'm glad you brought it up. Watch. What is the limit as x goes to 5 pi thirds of cosecant of x? Is cosecant continuous at 5 pi thirds? It is. So it's just going to be the function value, cosecant of 5 pi thirds. But I will ask you on a quiz to simplify your answer. So what is I can mask a unit circle question in terms of a limit. So real quickly, let's see what it is. Here's 5 pi thirds. The ordered pair is 1/2 negative square root of 3 over 2. Cosecant is the reciprocal of sine. So if you flip it, it's -2 over the square root of 3. Or when you rationalize it, -2√3/3. So yeah, brush up on your unit circle. I may throw one or two on the quiz tomorrow. Okay.
So can you give like a basic example? Is there a version where it's not continuous at unit circle?
Oh, well, anytime cosecant is undefined, so like when y is 0, so like cosecant of 0 is dne, cosecant of pi is dne, yeah. Oh, well, because what I mentioned yesterday is if it were a true free response, cosecant of 5 pi thirds is considered a numeric answer. You could stop on a free response, but I would ask you to simplify it, evaluate it. Yeah.
So if it does not exist, we can just put
Yeah. Mm-hmm. Yeah. Your quizzes are always short answer, but I could say simplify. Simplify. Yeah. I mean, I might ask you like 1 or 2 unit circle questions tomorrow. Yeah. And I wouldn't do that right now until we learn about vertical asymptotes. Okay. All right, here we go. Let's get through example 9. We got like 7 minutes. You can use the 3-step definition of continuity not just to determine if something is continuous, but for a question like this where you're finding unknown values of constants that make it continuous, okay? Because it gives you a checklist, right? So let's take a look at it. If f of x is this triple-headed Elmo, right? It's a parabola to the left of -1. It's the ordered pair -1, 4. And then it's to the right of -1, it's the line. Find the values of a and b, which are constants in the equations, so that the function is continuous at -1. Okay, well, let's go ahead and set up our machinery. The limit as x goes to -1 from the left of f of -1, and the limit as x goes to -1 from the right of f. And just like we would if there were numbers in the equations instead of some unknowns, we evaluate it by plugging into the correct piece that particular value. That's the function value. That's why solve either one of them. And you're subtracting one from the other. Plugged up into either one of the other. And that's it. You might actually do something. Like,